In lesson 4.1, we learned about discrete probability distributions. Now, in the second lesson from Learning Outcome 4, we're moving on to continuous probability distributions. This will conclude the new material you have to cover before study week. In this video, we're going to talk about Learning Objective 4.4, Compute Probabilities for Continuous Distributions, including the uniform, exponential, and normal distributions. This sheet will have the same format that you had when we learned about discrete distributions, like the hypergeometric, binomial, geometric, and Poisson distributions that we'll talk about what the distribution is, then do a couple examples from each one so you can see how they differ from each other. So before we get into these three continuous distributions, I just wanted to remind you that a continuous random variable is one that can take any value in an interval. The data is continuous. Usually we know that because it is measured. So when you measure a value, it can take on decimals. It's not something that you just count like a discrete value. The problem is because it's not something you can count like a discrete value, you won't be able to list all the outcomes in a table. For example, when we talked about flipping a coin, the possible outcomes were like heads and tails, and we know they had a 50-50 chance, something like that. We can't build this for a continuous random variable because if you're measuring something continuous like weight or height, people could have any decimal number as a measurement for their weight or height. This leads to an infinite amount of values that can't be listed in a table. So instead of listing all the possible options in a table for a continuous random variable, we use a graphical distribution. Basically, you draw as a curve what the probability would look like. We call this the probability density function or the PDF for the distribution. It uses function notation to represent the probability density function, so it is normally called f of x. Sometimes it's called p of x, but typically f of x, and it's used to represent the likelihood that you'll fall between any range of values for a continuous random variable. So it's the same idea as the probability density functions we did last class, where we listed the outcomes in a table, just because the values can take any interval, we can't possibly list them all that way, so we use a curve instead. Some properties of the probability density function are that they are represented using a curve. So if I draw a curve again, they don't all have to look perfect like this, but this would represent your PDF. Any probability can be represented as an area of the under the curve. So let's say this is the middle of the distribution and I want to find out the probability between, if I call this point C and I call this point D, it would be represented as an area under the curve. Whereas in a table, you normally have to add up the individual probabilities. In this case, when we talk about probability, we're always referring back to area. So how much probability is taken up in this drawing. Probabilities still need to be between 0 and 1 to follow the regular rules for probability. And we also know that for probabilities that when you add up all the possible options, they need to add up to 1. That means that the total area under this curve will also add up to 1 because you have to follow that regular probability rule. When you have 100% of outcomes, it will add up to 1. Also, when we talk about area, you can't have an area under a single point. If I just look at one point like C, there's no area under a single point. So we always talk about between 2 points or less than or greater than areas for continuous values. We don't talk about a single value probability. It's always less than, greater than, or between problems, which you'll see when we get to some of the examples. Finally, when we talk about probabilities in those intervals, they're usually written like this, like the probability that the continuous random value x is between C and D. This area I have shaded under the curve would be written as P, and then in brackets, that x is between C and D. Okay, now that you have that general information about a probability density function, and that's represented using a graph, and that for the graph, the probability will be the area under the curve. Now we can learn about three different probability distributions that have special properties and are named. The continuous distributions we'll learn about are called uniform, exponential, and the normal distribution. So the uniform distribution is used when you have a constant probability across an interval. So when you graph out a curve for a uniform distribution, it actually isn't a curve, it will look like a rectangle. And because the probability is constant across the interval, it's actually, you calculate the probabilities like you're calculating the area for a rectangle. So it's quite easy to get the probability. You'll just look for, let's say you want the probability of falling between 3 and 4. You'd look for that length or width, and you'd want the height. Those are the two things you'd normally multiply to get the area of a rectangle. For the height, you'll look for the maximum minus the minimum value to break it up. So you'd look at maximum as far as the rectangle goes to the minimum as far as the rectangle goes. The difference between them will be what we divide by. Some other conditions for the uniform distribution, all outcomes will be equally likely, and it does need to be a continuous variable, not a discrete variable, because otherwise we could just list all the options in a table and we wouldn't need to use the uniform distribution. In Excel, there's no specific uniform distribution function. You just calculate the area of the rectangle between any 2 points by taking the difference in the 2 points you're interested divided by the maximum minus the minimum value for the rectangle. There's a shortcut for the expected value and the variance that's written here. The expected value will be the max plus the min divided by 2. That will just be where the middle of the rectangle is. So for this one, it would be like approximately somewhere like here in the middle of the rectangle, approximately. And for the variance, you have to do the maximum minus the minimum squared divided by 12. We're not going to prove those formulas, but we can use them to quickly calculate the average and standard deviation. Okay, so let's do a quick example. The amount of time in minutes a person must wait for the bus is uniformly distributed between 0 and 15 minutes. So if we start at 0 and we go to 15, if it's uniformly distributed, whoops, there we go. That would be our rectangle. I didn't quite draw the axis straight, but something like that. If I correct my axis, try to draw it a little bit more straight. That's a little bit better. 15 to 0. We want the probability that a person waits less than 12 and a half minutes. So 12 and a half would be just a little less than 15. And if you want the probability they wait less than that, or fewer than 12 and a half minutes, it'd be everything less than 12 and a half. So how we find that probability using a uniform distribution is you would just take the difference between the two values you're interested in, which in this case are 12.5 and 0, because we're interested in anything less than 12.5, and you divide it by the length of a rectangle, 15 minus 0, again, because we're starting at 0 minutes. That probability will be 0.833333. So there's about an 83% chance that the person will wait less than 12 and a half minutes. On average, how long do they wait? That's just the middle between 15 and 0, which is 7 and a half. And how many minutes do they wait, or what's the spread of the minutes that they wait? That's the standard deviation. We can calculate the variance by doing maximum minus minimum to the power of 2 divided by 12, but that would be the variance. So that'd be measured in minutes squared. To get the standard deviation, you just take the square root of that to put it back into the original units. So on average, they wait about 7.5 minutes, but the standard deviation is about 4.33 minutes. So there is quite a bit of variation in the minutes you can expect to wait. I have another question. A total duration of baseball games in the major league in a typical season is uniformly distributed between 447 and 521 hours inclusive. So if you wanted to draw that one out, we're between 447 and 521. And the question says it's uniformly distributed. So that means it has this rectangular appearance. What is the probability the duration for the games is between 480 and 500 hours? So let's say 480 here, 500 here. We want this probability. It's an area of the rectangle. To get the area of the rectangle, we'll look at the difference between 500 and 480 for the length of the rectangle. For the height of the rectangle, we divide by 1 over 521 minus 447, the maximum and the minimum. That will give you this size because we know the area has to be 1 because for all probabilities it sums up to 1. So that's why we divide 1 over that difference in from the max to the min, and it gives us about a 27% chance. For the average, again, you just always follow the expected value formula where you look at max plus min divided by 2. That will get you exactly in the middle, which is about 484 minutes. And this question asks for the variance, not the standard deviation. So if you're just getting the variance, you just do the difference between max and min to the power of 2 divided by 12. And you don't need to do a square root if it asks you for the variance and not the standard deviation. So the variation would be about 456 minutes squared. And that's the uniform distribution. Like I said, it's basically equivalent to calculating the area of a rectangle. So there's no specific uniform distribution formula in Excel. You just have to use the formula x2 minus x1 divided by b minus a. Now we're going to move on to the exponential distribution. The exponential distribution models the time between events in a Poisson process. So basically, it's similar to our Poisson distribution where we had time between events, but instead of being discrete options for like how many possible times or waiting there is, in this case, there's continuous options. So what I mean by that is it's a continuous random variable that's represented in the interval. How you recognize the exponential distribution is you will have some kind of rate involved. So it'll be events given per unit of time. To use the exponential distribution, you do have to have a constant rate, so the rate cannot change throughout the question, and the events need to be independent of each other. Like when we checked independent probabilities, one does not affect the other, is what independence means. The exponential distribution doesn't look like a rectangle. It almost looks more like a curved triangle distribution. This is what it would essentially look like, but you still represent probability as the area under the curve. There is a function for the exponential distribution in Excel. It's expon.dist, where you enter the x value you're concerned with, the rate parameter lambda, that's this symbol here, that's given in the question, and always set the last argument to true. When you set it to true, that will give you the probability that you're less than a value. I'll show you what that means with an example. You can also get shortcuts for the expected value and the variance. For the expected value, the calculation will be 1 over your lambda rate parameter, and for variance, it's 1 over lambda squared. Okay, so let's look at some examples of how we can use the exponential distribution. Let X be the amount of time in minutes a postal clerk spends with a customer. The time is known from historical data to have an average amount of time equal to 4 minutes. Find the probability that a clerk spends 4 to 5 minutes with a randomly selected customer. So, in this case, we are given some information about the average amount of time it takes with a customer. That the time is known from historical data to have an average amount equal to 4 minutes. So 4 minutes per customer on average. That average value that it's giving you in the question on average is mu. Mu is 4 minutes. But we need lambda in the Excel formula. The Excel formula needs lambda, but we do know the relationship between mu and lambda. Mu is 1 over lambda. So if we want lambda, if we rearrange the formula for that, lambda would be 1 over the average, mu. So the lambda that Excel needs is 1 over 4. If the average amount of time, that's the expected value, mu, is 4, then lambda that goes into the Excel function expon.dist is 1 over 4 because the average and the lambda values are opposites. Then we're asked for probability between two numbers, the probability the clerk spends between 4 and 5 minutes. So to break this down, to make the question a bit easier for you, I've broken it down into a number of steps. Let's say we want the probability that they take 5 minutes. We would start with expon.dist, 5 minutes, lambda of 1 over 4, and cumulative set to true. You always set it to true. So what this means is actually 5 minutes or less is what the true part means. That this is giving us the probability of taking 5 minutes or less. It's about 71%. But the question doesn't ask us for 5 minutes or less. It asks us for between 4 and 5 minutes. So the next step is I'll find expon.dist for 4 minutes, lambda 1 over 4, cumulative, oh, true. And that gives me about 63%. And this is technically for 4 minutes or less. Then, if I want the probability of between 4 and 5 minutes, all I do is I find the difference between these two probabilities, between 5 minutes or less and 4 minutes or less. When I do the difference between those, I'll be left with between 4 and 5 minutes. I just subtract them to get between 4 and 5 minutes, and it's about an 8% chance of happening. Okay. Knowing if you have mu or lambda from the question is usually the trickiest part of the exponential distribution and how to figure that out, so let's do some more practice. The time spent waiting between events is often modeled using the exponential distribution. For example, suppose that an average of 30 customers per hour arrived at a store, and the time between arrivals is exponentially distributed. On average, how many minutes elapse between two arrivals? So the question's asking us to find the probabilities for less than 1 minute and more than 5 minutes. But when we look at the question, we're told an average of 30 customers are served per hour. Because you want the probabilities per minute, we must convert that into how many customers are served per minute instead of per hour. So if 30 customers are served each hour, basically there's 60 minutes in an hour and 30 customers you serve. So it's 2 minutes per customer is the average. Instead of writing it as 30 customers per hour, another way you can write that is that it takes 2 minutes per customer since an hour is 60 minutes long. Then just like we did for the previous example, you can calculate lambda, what you need for inside of the exponential dist function by doing 1 over mu, the average. So it would just be 1 over 2. So the lambda is 0.5. Then if you want to find the probability following the exponential distribution that a customer would be served or arrive in less than 1 minute, you'd use the exponential distribution function, put in the value from the question, 1 minute, use your lambda, and always set cumulative to true. There's about a 39% chance of that happening. If you want to find more than 5 minutes, I'll start by just doing expon.dist, the value from the question, the value of lambda, 1/2, and cumulative true. But if you set cumulative true, that always gives you a probability of less than the amount from the question, 5. I don't want less than 5, I want more than 5. However, it's not hard to get the probability of being more than 5 instead of less than. To do that, just use the rule of complement. Remember, the rule of complement says do 1 minus the opposite. So if I want more than 5 instead of less than 5, I just do 1 minus the answer we got. And by the rule of complement, the probability of more than 5 minutes will be about 8%. So the uniform distribution deals with constant probability across an interval. It doesn't change. Exponential distribution deals with units of time, like the average amount of time in the first question to serve a customer, the average amount of customers that arrive at a store. The next distribution we're going to look at is the one that we're going to be using for the rest of the course. So although the uniform and exponential distributions do have applications in business, the most important one to know and to use for the rest of the semester will be the normal distribution. So for the rest of the lesson, we're going to focus on just the normal distribution since it's the most important one in business applications. So if you look at values in nature, anything related to sums or totals or averages, you get a very characteristic shape. So here are people in the military lined up according to height. If you try to draw a curve over their heads, it might look something like this. These are real SAT scores. Someone drew a curve in blue over it. And these are real blood pressures for systolic and diastolic blood pressure. Again, if I draw a rough curve over the bars in the histogram, they look like this. So in all of these cases, you're getting this peaked curve that's quite flat, then it's more steep in the middle, and then it goes back down to flat at the ends. And this shape happens over and over and over again for things measured in nature, like height, blood pressure, and test scores. It's so important that this distribution has its own name, and it happens so often, they call it the normal distribution. The reason it's called normal is because it normally appears whenever we're analyzing these types of measured variables like height, weight, blood pressure, etc. It's a continuous probability distribution that's known for its bell-shaped appearance. The reason they say it looks like a bell is if you were to draw like a little Christmas bell, it has a little chime, a little thing to attach it. If we just talk about this part, that's what the normal distribution looks like. This piece here, kind of a curved bell shape. It's also unimodal. When we talked about histograms, what that meant is that it has one peak in the middle. So unimodal. And it's supposed to be perfectly symmetric, which means that one side matches the other around this middle piece. The normal distribution is completely defined by its mean and standard deviation. Those are the only two things you need to model a normal distribution. It will always be symmetric, continuous, and bell-shaped, and there is a formula for it in Excel. It's norm.dist, where you enter the value from the question X, the mean, the standard deviation, and just like for the exponential distribution, we always set the last argument to true. That will give you the probability that you're less than X, the value from the question. The expected value is just the mean, and the variance would be the standard deviation squared. The normal distribution will look slightly different depending on what the mean and standard deviation are. If you click on the link that's given in the notes, it opens up this graphing calculator that allows you to see how the shape of the normal distribution changes. In this example, we have an expected value of 30 and a standard deviation of 3. If you change the mean from 0 all the way up to like 50, when you change the mean value, it actually changes the location of the normal distribution, so where the middle of it is. If the mean is 5, then the highest peak for that unimodal peak will be at 5. If the mean is 30, let's go up one more, then that highest peak is at 30. What the standard deviation does is it changes basically how tall or how flat and peaked the distribution is. If you have a really high standard deviation, then the distribution is much more spread out. If you have a very low standard deviation, then the distribution is much more pointy and peaked. So changing the mean moves the location, Changing the standard deviation changes the shape of the normal distribution. The normal distribution is not just one distribution, it's what's called a family of distributions. What's meant by that is the normal distribution always follows certain rules, like it's symmetric, continuous, and bell-shaped, but depending on the mean and the standard deviation given in the question, the normal distribution you're talking about might look different. The mean changes the location, the standard deviation changes the shape, how peaked or how flat the distribution is. We're going to do some examples of normal distribution calculations. These three are kind of the basics for any type of probability question you could ever be asked related to the normal distribution, because there's really only three types of questions you can have for the normal distribution. Questions that ask for less, questions that ask for more, or questions that ask for between. We're going to do one of each. I always find it helps to draw pictures to help with the normal distribution calculations. So I'll draw some pictures to help you see how these work. We have final exam scores in a statistics class are normally distributed with a mean of 63. Like I said, the mean controls where the middle is. So that's the mean. And the standard deviation controls how peaked it is. So standard deviation is 5. Actually, I should probably just make this bigger. And then I can put different colors for the different parts of the question. So mean is 63, standard deviation is 5. The first question says, find the probability a randomly selected student scores less than 85. So if 63 is in the middle, 85 is bigger than 63, so it might be somewhere over here, 85. If we want the probability they score less than that, it'd be everything under the curve. Since probability is equal to area under the curve, they're the same thing. Less than 85 is somewhere in there. If I want that probability, because the question says the scores are normally distributed, I use norm.dist. I use the value from the question, the mean from the question, the standard deviation from the question, and put true for cumulative. And that's it. Your probability will be about 100% chance that the student scores 85 or less than 85. If you have a more than question instead of a less than question, I'll use a different color for it. More than 65. 65 is just above the average, and if we want more than 65, it would be everything bigger on this end. So for less than, we could just use norm.dist. For more than type questions, you can use norm.dist. The value from the question, 65. The mean, 63. The standard deviation, 5. And cumulative true. The problem is when you write cumulative true in Excel, it always gives you the probability of being less than. So technically, this would give the probability of being less than 65, not more than 65. So for more than questions, you have to use the rule of complement, which says that probabilities need to add up to 100%. If you want the opposite, just do 1 minus. So if I do 1 minus the less than probability, I'll get the more than probability, and it will be about 34.4%. So anytime you have a probability from the normal distribution question that asks for more than, remember that rule of complement, 1 minus, and that's how you find the more than probability. Finally, we have a between question. These are kind of like the ones we did for the uniform distribution. 62 is less than the mean, and 70 is bigger than the mean. So one goes on the left and one goes on the right, all depending on what the value is in relation to the middle, 63. So I'd be looking for this between area, between those two numbers in orange. For any between questions for the normal distribution, how you answer them is you use norm.dist for the bigger value first, and then you subtract norm.dist for the smaller value, 62. The mean is still 63, standard deviation is still 5. And that's how you'll always do between questions. So if we want between 70 and 62, 70 is the bigger number. So first we do a norm dist with 70. 62 is the smaller number, so we subtract a norm dist with the smaller number, 62, and that will give you the between probability. That's about half, or 50%. Okay, and those are the three types of normal distribution questions you can really have: less than, more than, or between. If you can do those three, you can basically be ready to solve any other type of problem. The last step is a learning check question where I'm going to ask you questions about each of the distributions, but these ones are more mixed up, so you'll have to carefully think about which probability distribution to use in which situation. Please pause the video here, and when you come back, I'll show you the answers. Okay, so for the first one, it does say the time it takes for students to complete an exam is normally distributed. So this one will be a normal distribution. To find the probability the student finishes in less than 75 minutes, for less than questions with the normal distribution, all you do is you put in the value from the question, less than 75, put in the mean from the question, put in the standard deviation from the question, and true for the cumulative setting, meaning less than 75. That gives you about 15.8% probability. The next one, if you gave it a try, we're told the time customers arrive at a coffee shop follows an exponential distribution. Notice it's related to time, just like the Poisson distribution, since an exponential models the Poisson process. We're told that the mean is 4 minutes long. What is the probability the next customer arrives in 3 minutes? Remember that if the mean is 4 minutes, then lambda must be 1 divided by that mean. They're always opposites, like 1 over each other. So if I want to use expon.dist for the exponential distribution, my value from the question is the next customer arrives in 3 minutes. The lambda value is 1 over 4, and I'll set my cumulative to true. And that gives me a probability about 52.76%. For the third question, we're told that this amount of time a bus arrives at a stop is uniformly distributed. So this one's the uniform distribution. Usually it takes 10 to 20 minutes. We want the probability the bus arrives between 12 and 15. So I would do 15 minus 12 divided by the max and min difference. 20 minus 10, that's going to give me 30% chance. And finally, I threw in another normal distribution question just because the normal distribution is the most important one in the course. For this one, we have IQ scores that have a mean of 100 and a standard deviation of 15. We want the probability a person scores between 85 and 115. For that, any kind of between question, you'll have to do it twice. First with the higher value, mean, standard deviation, true, and then you'll have to do norm.dist a second time to subtract with the lower value, the mean, standard deviation, and true. With that difference, that will give you the probability that's between the two numbers, which is about 68.3%. So I will upload this spreadsheet. You can access it and download it from Moodle with the answers if you need to actually click in any of the cells to see the formulas. Moving forward in the course, your most important distribution will be the normal distribution. We'll keep using it for the rest of our course time together. So if you can follow along with how that norm.dist function works in Excel to be able to get these different probabilities, less, more, or between, that's the most important thing for this first objective we're covering today. In the next two videos, we'll talk more about the normal distribution for learning outcome 4.5 and 4.6.